This is the first lecture out of the Thermochemistry chapter, chapter 6. And I'll start with the simple definition of thermochemistry. And it's basically the study of the energy changes that accompany chemical reactions. And another basic definition of energy. Energy is defined as the ability to either do work or to transfer heat. And an equation that is often used to represent a change in energy. So change in energy, delta E equals Q, which is heat, the transfer of thermal energy, plus work. And you'll see in a moment that work is defined as energy used to physically move an object. The units that we will primarily use for energy are Joule, abbreviated with a capital J. And a Joule is defined as the amount of energy needed to move 1 kilogram at a speed of 1 meter per second. Another unit that we will see frequently in chemistry is the calorie, and that used to be used more years ago. It's more commonly Joule now. Calorie is the amount of energy needed to raise the temperature of 1 gram of a substance, 1 gram of water, by exactly 1 degree Celsius. And the conversion between Joule and calorie, and you'll see this quite a bit, 4.184 calories equals 1 joule. Some other vocabulary that you'll be hearing in thermochemistry is reference to the system and the surroundings. So the system is typically the chemical reaction that we're studying. And you could look at the picture over here and think of these molecules or elements. And the surroundings is anything around the system that it could possibly transfer energy with. So we're primarily concerned with the transfer of energy, which is what occurs with every single chemical reaction. And just as a reminder, if energy is transferred and causes an object to physically move, that energy transfer is referred to as work done. And on the other hand, energy that is transferred that causes the temperature of an object to increase is called heat. And so heat is the transfer of thermal energy. Thermal energy is actually a form of kinetic energy because thermal energy causes particles of a substance to move faster, and that's what generates the heat, which then causes temperature to increase also. So heat, again, let me just emphasize, heat is the transfer of thermal energy, okay? It's transfer of thermal energy. And heat always flows from a warmer object to a cooler object. There's no such thing as cold, for example. Cold is just the absence of heat. So if you open the door to your house and it's cold outside, it would be correct to say the heat from your house escaped. It would not be correct to say that the cold rushed in. It's the heat escaping. Okay, so when you have two objects at different temperatures that are touching, the heat will flow from the warmer object to the cooler object until thermal equilibrium is reached. Thermal equilibrium simply says is reached when objects are at the same final temperature. So heat will continue to be transferred until the two objects are at the same temperature and therefore are at thermal equilibrium. You may well have already heard of the first law of thermodynamics, which is conservation energy. It sounds very familiar to conservation of mass. It says energy is neither created nor destroyed, Another way of saying that is that the total energy of our universe is constant. So if energy of a system that we're studying is lost, for example, the surroundings have to have gained that energy. Okay? Energy can neither be created nor destroyed. It ends up perhaps in a different form or a different place, but the total amount of energy is constant. The last concept I'm going to explain in this introduction to thermochemistry is the concept of endothermic versus exothermic processes. And endothermic process is a process where the system that we're studying, typically a chemical reaction, where energy flows into that system. The energy of the system increases over time. That is called endothermic. Now, mathematical signs in thermochemistry are very, very important. And by convention, and it also makes sense, if you have an endothermic process, we use a positive mathematical sign to indicate that. Same thing this is saying here. For an endothermic process, change in energy is positive, okay? And that's simply because the system has gained more energy. Another way to look at it, and a way that you should get somewhat familiar with, if you look at a graph of an endothermic reaction, so notice that we have energy along the y-axis, and along the x-axis, you can think of it as either time or progress of the reaction. But you can see in this graph representing an endothermic reaction that the energy of the reactants are lower than the energy of the products. In other words, the system, started out as reactants, has gained energy in order to become products. So that's classic for an endothermic reaction. Now, an exothermic reaction is just the opposite. In an exothermic process, the system we're studying, chemical reaction typically, is releasing energy to its surroundings. So the energy of the system itself is going down, and we designate that mathematically with a negative sign. Looking at the graph for an exothermic reaction, the energy of the reactants is higher than the energy of products because, of course, energy is released from the reactants as they proceed to products. That's it for introduction to thermochemistry, and the next lecture is calorimetry, which is a method scientists use to measure energy transfer, heat transfer.